The first example I put on linear programming, I took it out of the book and just kind of wrote down the steps. Now, most of this is done for you, so I want to just kind of start by giving you an example of what the linear programming problem looks like. And there's only one extra part of it past what we were doing in the previous section. So, first of all, this problem, what you want to do is after you read the problem, you want to try to figure out what your variables are, and then you want to try to organize everything in a table. Some of these problems, the table would be given to you, so it'll help you out a little bit there. So when I read through this, I'm just going to identify the key things. First of all, it says that you have two types of tents. Okay, you have a standard and you have an expedition model. Those are probably going to be your variables. Okay. The hardest part of these problems for most students is setting everything up, so always read the question. The question says, how many tents of each type must be manufactured? So whatever the question is will tell you what the variables are. So what I'm going to do is I'm going to let X be the number of standard tents made per day, and then Y is the number of expedition tents. Okay, the variable shouldn't be a mystery to you because the question will tell you what it is. Okay. And then when we start reading this, what it's going to say is it's going to say when you have a standard tent, it's going to require 1 labor hour for cutting and 3 for assembly. So if you look at the way I put this together, it's going like this. You have the standard model, and if you read what that said, it said the cutting department takes an hour and the assembly takes 3 hours. That's what that says. If you read on, then it's going to say each expedition tent requires 2 labor hours for cutting and 4 labor hours for assembly. Okay, so that's what's given in that. And then there's usually some what we call constraints, which is the labor hours. So it says the maximum labor hours available is this. It says for cutting, there's 32 hours. Okay, that's what that says. And then it says for the assembly, there's 84 hours. So see, there's kind of your inequality right there. You're going to have an equation for the cutting department, less than or equal to 32. Then you'll have an equation for the assembly, less than or equal to 84, like this. What's different about this, though, is this. This is what makes it a linear programming problem. It says if the company makes a profit of $50 on a standard tent, which is given there, and $80 on an expedition tent, then it says how many of each should you produce. Okay, this is an optimization problem, is what we call this in business, where you're trying to figure out the optimum number of things to produce given these conditions. You're always going to have labor hours is always a condition. No business has infinite labor hours. That's a constraint on your ability to produce things. Okay, so what you do is you're going to get, this is what's different, is you get what's called an objective function. The objective function is what you're going to plug corner points in, and the objective function is profit. So the profit said you're going to make $50 for a standard tent and $80 for an expedition tent. So you would just say 50x plus 80y is your profit, because again, x is the first type of tent, and then y is the second type of tent. So your profit is 50x plus 80y. Okay, the problems we did previously had nothing to do with that. Now what happens is your inequalities go like this. If you organize the chart, then it's going to go like this. The standard model's x, the expedition's y. So this first row is just going to be 1x plus 2y less than or equal to 32. You have less than 32 labor hours. The second row is going to say 3x plus 4y is less than 84 because you have 84 labor hours available in the assembly department. The other thing you're going to have is x is greater than 0 because x is the number of standard tents. There's no such thing as a negative number of tents. And y is greater than 0 because there's no such thing as a negative number of expedition tents. Okay, what you're going to do with this problem is what I just taught you. You're going to graph that, find the corner points, but what's different is the corner points are going to be plugged into the objective function, and we're going to see which one produces the most profit. That's the idea. So the only thing that's new on this is that one little piece of the problem. Now I'm sort of talking you through this problem. I've done most of the work for you. On the next page, this is what you get. You write your linear programming problem like this. You say that you're going to maximize the profit. That's called the objective function. Okay? The inequalities are your constraints. Okay? So those are your constraints. And then these are called the non-negative constraints. X and Y both have to be positive because it's the number of tenths being produced. Negative makes no sense there. Okay? So what you would do is graph. I'm not going to go through the details of the graphing, but if you went through the graphing, you would find that you would have this feasible region. You would find that you have corner points 0, 16, 28, 0, and you would use a matrix to do that, like I showed you before. The 0, 0 would be another corner point, so you've got to figure out your corner points. Now, everything I've done here, we did in the previous section. Everything, the graphing, the corner points, all of that kind of stuff. Now, here's how you finish this up. So once you get your corner points, which are 0, 0, 28, 0, now I'll show you how to finish up the problem. You have 0, 16, and 26. Now that 26 came from a matrix, but I'm not going to do that because I've shown you how to do that. Now here's what you do. The objective function in this problem was P equals 50x plus 80y. And if you read the problem, that 50 just means $50 per, and I forgot what my tenths were. We had like standard and expedition, okay? So it was 50 per standard tent, and that was $80 per expedition tent. So here's what you do to finish up linear programming problems. It's real easy. What you do is you just plug in the corner points into the objective function. Okay, the first one, if you did 0, 0, you'd have 50 times 0 plus 80 times 0, which would be $0. So you're not getting any profit off of making nothing, obviously, right? Then you can take the next one, which is 28, 0. Okay, X is 28, so you would do a profit of 50 times 28 plus 80 times 0, and you would just take your calculator and do that. So if I do 50 times 28, that would give you a profit of $1,400 if you only produce 28 standard tenths and forget about the expedition. Okay? The next corner point is 0, 16. The meaning of that is you're making no standard tenths, but 16 expeditions. So your profit would be 50 times 0 plus 80 times 16. Okay, I do that on the calculator, compare the profit. So 80 times 16 is a profit of $1,280. Okay, now you have one other corner point, which is 26. And if we did this, we would do $50 for the 20 standard tenths plus $80 for the 6 expedition tenths, and we'll see what we get out of that. So 50 times 20 plus 80 times 6 is going to be $1,480. Okay, so here's what you have is that's your maximum profit because that's the biggest. Okay, so the optimum solution to this problem to a business would be that you need to make, what you would conclude is you would say we need to make 20 standard tenths and we need to make 6 expedition tenths. Okay, and that's because we have labor hour constraints on this, and because of those labor hour constraints, that's going to tell us where we're going to maximize out our profit. Does that make any sense? Now, everything in that problem is the graphing of the inequalities, finding the corner points, but the last part of linear programming is to evaluate the corner points and see what maximizes something. Okay, that's the idea. That's the only thing that's different on the problem. So what I'm going to do on the next kind of problem, what I will test you over, because of us missing class last Wednesday, is that the only kind of linear programming problem I'm going to test you over is this, just for this test. And that will be, I give you the situation. What you do is you get, you got to do the graph. You got to figure out the corner points. you've got to evaluate the corner point. So I'm not doing the word problem because I don't feel like there's time for you to get that down as good as I would love. Okay? But I will test you over this kind of thing because it's not hard to learn. Okay? The word problems and stuff, we'll do that later. Probably what I'll do on the test is I'll do a word problem, linear programming as extra credit. Okay? And if you can do that, that will be a good thing. Okay? Because all you'd have to do at the word problem is set up the conditions. Okay? And usually that's the hardest part of the problem. Okay, so what we're going to do on this one then is we're going to graph these two inequalities. I'm going to just kind of do the scratch work over at the side. We have 2x plus y less than or equal to 10. We have x plus 2y less than or equal to 8. So we're going to do that, all right? Now what you want to do is just do the intercepts in your head. So what's the x-intercept on the first equation? 5. What's the y-intercept? 10. Okay, you got that. All right. Go to the second equation. Again, try to make these so that they're fairly easy to do in your head. What's the x-intercept? 8. And how about y? 4. Okay, so we're going to graph those things. All right. So you want to go ahead and get the corner point. I'll give you kind of a nice graph like this. I'll make the numbers pretty easy to deal with. So let's just go out to 5. 1, 2, 3, 4, 5. And then 6, 7, 8, 9, 10. And you can do that in both directions and that'll be fine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 like that. Okay, and what we're going to do is just like we did previously. We've got these things. We have a less than or equal to, which is going to tell you two things. Solid line below. Okay, so on this first graph, we're going to put a x-intercept of 5, y-intercept of 10, solid line, and just know that you're below. Okay, the second line, I'll do a different color. We're going to do again, it's going to be solid, and it's less than, therefore it's going to be below. Okay, so we'll do kind of what we did before. Just put a dot on 8, put a dot on 4, connect the dots, and this one is going to be below. So where am I? If I'm below both lines, where am I? I'm at the very bottom corner, right? Okay, so you're below the green line and the red line at the same time, so that's where you are. Okay, that's it. Is everybody getting that down okay? I can tell you're getting the x-intercepts and y-intercepts down, but how about the feasible region? Below is far that way. Above would be that way. Okay, that's what you got to pay attention to. Okay, now let's do the corner points. Remember, some of these things you'll be able to do in your head. Maybe one of them you have to do a matrix on. So you basically have these corner points. Okay, this corner point here would be 0, 0, which is going to give you minimum profit. This one right here is 5, 0. This one here is 0, 4. And then what you're going to have to do is use a matrix to find this one then. Okay, so I'll just put this in the calculator. If you want to do that, you can. So what I want to do on that is just put the system in my calculator like we've been doing. So I'm going to edit over this 2x3 matrix. Again, what I'm doing is I'm doing the two equations I got highlighted in yellow there. So I'll have a 2x3. The first row is 2, 1, 10. And you want to do this, you don't want to always go by looks. The second equation is 1, 2, 8. And then you want to put that in reduced row echelon form. Okay, so we'll have that as our matrix put in. And then we want to just go to the reduced row echelon form. Okay, just go down to the RREF button. Oops, I got to get that on a clear screen. Sometimes I forget that. So I want to go matrix, math, reduce row echelon form, then go back to matrix A or wherever you put it. And you can tell me if you got what I am. You guys are faster at this than I am. 4, 2, is that good? Okay, so that matrix ended up giving us the reduced row echelon form, basically of 4, 2 then. Okay. So that gives that corner point of 4, 2. All right. Okay. Is everybody with me? And this is the kind of thing I'm going to test over, is something like this, okay? You can do this okay, I think. Now, here's what you're going to do. You're going to take the objective function, p equals 5x plus 5y. Now you're maximizing so that you don't really have to do that one. I mean, that's always going to be the minimum one. You can just forget about the 0, 0. Let's just do the 0, 4, the 5, 0, and the 4, 2. And don't make an assumption that it's always going to be the one you did the matrix on. It will not always be that one. So you plug in. So you would have the profit is 5 times 0 plus 5 times 4 on the second one, so that's 20. Then plug in the second corner point, so that's going to be 5 times 5 plus 5 times 0, so that one's 25. And then the last one is going to be 5 times 4 plus 5 times 2. So let's see, that's 20 plus 10, so that's 30. So that means the answer to the problem is the 30. Okay, so what you do on linear programming is you take the corner points of your feasible region, plug them into the objective function, and if it's a maximizing problem, that's the one that's the biggest. That's it. That last step, there's nothing to it. Okay, if you got the graphing down and the corner points down, then there's nothing to finishing it up. Okay, you understand what I'm saying by that? Okay, all right. So the key thing is the graphing and the corner points and the evaluation. Okay, all right, any questions about that? Okay, so this is what I'm going to have you do. This is the, since we missed last week on Wednesday, I'm going to have you do something like this. I'm going to do another one, another couple of these things. And I'm going to have you maybe try one in a minute and just kind of see if you're pretty successful in doing one of these. So let's do one on this one. This is the same idea. I give you a condition, so I'm going to just do the graphing over here. You can go ahead and start your graphing if you want to. Okay, so I got 4x plus 3y greater than or equal to 24. 3x plus 4y greater than or equal to 8. Okay, so let's just do our intercepts. So on the first equation, what we're going to have is it's a greater than problem. So you're going to end up being above, and you're going to end up being solid on that one when you do your graph. Okay, the intercepts. The x-intercept on this would be 6. The y-intercept on that would be 8. Okay, I'm going to do the same thing with the next one. Again, it's a greater than, so it's going to be above the line, and it's going to be solid. Okay, all right. And let's see, the intercepts on this, the x-intercept, what is the x-intercept on this one? 8 over 3. Okay, if you can't do that in your head, then write down 3x equals 8. Divide by 3, so you would get x equals 8 thirds. And if it's something like that, you can just take your calculator and change it to a decimal. So 8 thirds is about 2.7. Okay, the y-intercept on this would be 2. Okay, they will turn out to be decimals sometimes, and that's okay. All right, so let's go ahead and let's get our graph put together, and then kind of figure out our corner points. So let's see, we can just take this out probably to 8 is the biggest we need to take this out to. So I'm going to just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in both directions. Okay, and then I'll put the first one together. So the first one had an x-intercept of 6, and it had a y-intercept of 8. Okay, so you would connect the dots, and you would be above because it's a greater than problem. Okay, so a little bit different situation on this one. The second one, let's see, the x-intercept's about 2.7. So you can estimate where that is. You have a y-intercept of 2. So it'd be like that. And then you would be above. Okay, so those are your two lines. So where am I going to be? If you're above both lines at the same time, where am I?
Big area.
The big area, right. You're way out there. Okay, so your shaded region is going to be out here. Anybody have a question about that shaded region? above both. Anytime you're greater, then it's going to be up in the big area. If it's less, it's going to be down in the corner like that. Okay? So we have that. So what we would end up having is this region really kind of looks like this. I'm just going to kind of draw a picture of this. The corner points are going to be this right here, which is the point 0.8. So that would be one of your corner points. The other corner point would be this thing right here, which is, that was, I think, 6, 0. Okay, and those are the only two corner points you have. Everything else is just that infinite region right there. Okay, so you don't need to use a matrix on this when you do this then. Okay, so what do you do with the corner points? You work with the objective function, which is z equals 8x plus 7y. Now this problem says minimize and maximize, so you're just going to tell me what the minimum is and what the max is. Okay, so the first corner point is 0.8. When you plug in, you're going to have z equals 8 times 0 plus 7 times 8, so that's 56. Okay, the second corner point is 6, so that's going to give z equals 8 times 6 plus 7 times 0, so that is 48. Okay, so what's the max? The max is 56. The min is that. That's the answer to your problem right there. One of them's minimum, one of them's max. Okay, on that problem, I'm saying to find both the min and the maximum like that. Okay, does everybody understand that last step? Plug your corner point into the objective function. Okay, the objective function's always given in these problems, okay, the ones that we're going to be looking at here. Okay, any questions? All right, see if you can do this next one. This next one's pretty standard. Just start off by doing the graphing, find your corner points, evaluate your corner points, and see if you can get this one okay. All right? What did you get on your matrix? Did you get 2, 4? Those of you who've got done the matrix?
Yeah.
That's what I think it should be. At least that's what it looks like. Now you're maximizing on this problem, so you're just going to give the number that's the biggest when you plug your corner points in. Okay, well, anybody got anything? Anything yet? 14? Okay, all right, okay, all right. So there's what you want to check up here, and the first thing you want to make sure that you've done correctly, of course, is your graphing. And this first equation, you have an x-intercept of 4 and a y-intercept of 8, so that's the one that's in red. And then the second one, you have an x-intercept of 10 and a y-intercept of 5. That's the one I have in green. Again, you're below both, so it's a less than, so you're going to be down in this corner down there. So your corner points, you could figure out 4, 0 from looking. That one's the 4, 0. And then this one is the 0, 5. Then the other one comes from a matrix, so you'd have to put that matrix in your calculator to get 2, 4. Okay? And then notice what I've done on that is I've just taken the objective function. You don't have to worry about the 0, 0 because that's going to be where your minimum is in this. So you just plug in the 0, 5, the 2, 4, the 4, 0. When I plugged in 0, 5, I got 10. 2, 4 gave 14. 4, 0 gave 12. So that's where the max is. The min would be 10, okay, on that. So that's the end of the problem. What you're doing is just plugging the corner points of your feasible region in. That's the idea. Okay? Any problem with graphing or shaded region, any of that stuff? It's okay? Okay, all right. All right, because most of these things you'll just be doing using the intercepts on to do the graphing, and that's a fairly simple way to do it. That way you don't have to worry about slope and stuff like that. Okay, so 14 is the right answer on that. Any questions about that? Okay, that's what I want you to do on the test is one of these varieties of problems. So I'm going to go ahead and do ones that have 3 equations now and work with that a little bit. And then we'll kind of close off by putting it all together, one of these word problems. But I'm going to limit what I do on the test to just the 2 equations like you just did. So any of those kind of situations. So let's go ahead and put this one together on the next page. This one, the only difference is it has 3 inequalities. So we're going to have to do 3 lines, but we're still going to figure out the feasible region then. So let's start by thinking about how our graph goes then. All right, so let's see. I'll have x plus 2y less than or equal to 6. So the x-intercept is 6. The y-intercept is 3, and then you're going to be below on this one, okay? So let's go ahead and just kind of get the graphs put together as we go through this. All right, so let's see. Let's just go by 5s like we've been doing. So 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10. Go out further if we need to. And whenever you're doing the graphs on these, you want to be real accurate so that you can clearly tell where your feasible region is. So I'll do this one in red. So I'm going to do an x-intercept at 6, a y-intercept at 3, and I'm going to be below. So I'm going to put a few little arrows to indicate that it's less than, so I'm below. That already eliminates a lot of possibilities on this. Okay, so that's the first graph. Second graph is x plus y less than or equal to 4. I'll do this like in blue. Okay, so the x-intercept on this is 4. The y-intercept on that's also 4. So I want to go ahead and put that in. X-intercept 4, y-intercept 4. And then connect the dots on that one. This one you're also below on. Okay, so right now you would be below both of those lines at the same time. So you want to just kind of make a note to yourself that you know you're below that. So you're below both of those at the same time. Okay, and then the last equation is 2x plus 3y greater than or equal to 12. Okay, the x-intercept on this one is 6. Y-intercept on this one's 4. And now this time you're going to be above. Okay, so we want to get that graphed. So I'm going to put a x-intercept of 6, then a y-intercept of 4. Is that the same? Hold on. Did I do something wrong?
No. That's right. You're right.
They are the same line. Okay, well, that's okay. I just didn't realize that when I took this problem out of the book. See, like if you took 2x plus 3y is equal to 12, and if you divided, no.
They're 6 and 4, not 6. Yeah, they're the same exactly.
Oh, they're not the same. They have different y-intercepts. Okay, I'm not seeing very good here. Okay, so I've got a x-intercept of 6 and a y-intercept of 4, like that then. Yeah, okay, so this one goes like this. Okay, all right. Now, let's see. I need to zoom on this because it can be a little hard to kind of determine where you are on these problems sometimes. Okay, so that's what I've got on this. Now, what you have in this problem is you're also above that line at the same time. So this is actually a real simple problem. Okay, what you have to do on this one is you've got to be above the green line and below the other two. Can that happen?
No.
It can't happen. It's impossible. Okay? Because what you have to do is all these things have to overlap. So if you're down here, you can't be down there and up there at the same time. So there's no solution. This problem has no solution. There's no feasible region on this. Now that can happen sometimes on these problems. Sometimes you just have no, what we would say is there's no feasible region. So there's nothing that you could shade on that. So it would be no solution. Okay? You can't be above the green line and below the other two at the same time. Yeah.
So if those lines were flipped, we would have to put it would just be a 3 by 3 matrix, and we'd have to find that.
Yeah. Yeah. If you had 3 lines and you had an intersection point, you would just have to put in the 3 equations in your.
What would the corner points look like?
What's that?
What would the corner points look like for that?
Well, on that one, the corner points would be if it was this big region, it would be there and there.
Right. Oh, because it's everything below.
Yeah, yeah. But this one doesn't have a solution. There's nothing. There's no way where all these things come together at the same time. So that would be the idea. That one has no solution. Okay. All right. Let's see. Let's go ahead and see if you can put this one together, and do this one. Now you've got 3 lines. Now it's all less than, less than, less than. So if all 3 are less than, where are you going to be? You're going to be down in that corner, right? So go ahead and get the graph on this and see if you can finish this up. And I'll show you how to do the matrices on this in just a minute here. But let's just kind of get your graphs put together. So you've got 3 graphs that you got to do. So go ahead and do that. And I usually like to just get all my intercepts and everything put together first on these. And then that'll help me to kind of decide how to scale my axis and everything.
I think it definitely goes up to like 15 places in the X.
What's that?
I think it definitely goes up to like 15 places.
Just take it. We may have to scale it a little different. You have to scale it a little bit different is what we're going to do. You can either extend it or you can scale it a little bit differently. Because it looks like on this problem, your y-axis needs to go to 21 and so does your x-axis. Okay, and that's kind of designed so you can do your intercepts pretty easily. How many points are there on this? Yeah, let's just take it out further. Let's draw it big, okay? That's what I do, all right? So I'm just going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then just go out a little further. That's good enough. Okay, you can take it out 20 like that and so forth. So if you take it out like that, that's good enough. Or you could rescale. You know, there's different ways to do that. So let's see. The first one will have x-intercept of 7, y-intercept of 21. So we got that. And let's see. The second one, we have an x-intercept of 9, y-intercept also of 9. So it'll go like that. And then the last one will have x-intercept way out at 21, y-intercept of 7 like this. Sometimes when you're doing these problems, it's a pretty good idea to use a ruler because you can get off track on this if you try to freehand them. So it'll kind of look like that. And try to draw pretty big, and I just use a straight edge or something to do that. So anyway, since they're all less than, what that means is you're going to be down in this region right here. If they're all less than, you're always going to be in that corner like there. That's the most common application that shows up is like that. Okay? So we got the intercepts. It's all less than. We're there. Now let's just kind of look at how you're going to have to figure out these corner points. Okay? Now what you're going to end up having is you're going to have a figure that kind of looks like this. You're actually going to have these corner points. You're going to have this. I'll try to draw these real dark. You're actually going to have 5 corner points on this problem. Okay, you kind of got a situation that looks like that. Okay, those are your corner points. So you're going to have 0, 0. This corner point right here, that was the x-intercept, I think, of 7. So that one's 7, 0. And then this one was the y-intercept of 7. So that's 0, 7. Okay, now what you have to do is you have to do matrices on this. This is the reason why I'm color coding it, so you can kind of put this together. This one right here is the intersection of the green with the blue. Okay, so the matrix on this would be 1, 1, 9, 1, 3, 21. That would be how you get that corner point.
So you don't use it a 3
No, you got to do 2 at a time. Okay, because you won't get anything if you do that. The other one is the green and red. So this one is going to be, the red one is 3, 1, 21, and then the green one is 1, 1, 9. You just got to keep track of which equation is being intersected on that. That's why I use colors. Okay, so let's put a couple of these things in and just see kind of what we get on that. Okay, and you can just, they're both 2 by 3s. I'm just going to type over what I already have. So the first one is 1, 1, 9, and then 1, 3, 21. Let's see what that one's going to give. Okay, so I'm getting 3, 6 on this one. Okay, so when I put that in the calculator, I got 3, 6. Let's see what the other one is. Has anybody got the other one yet? What'd you get? 6, 3? Okay, I'll take your word for it. Okay, got to be kind of careful. Just put them in. Okay, so we got those then. So that would be your corner points, and you're doing maximizing on this. So what makes this different is now you have 5 corner points. Okay? So what you would do on this, since you're maximizing, you can just forget about the 0, 0. That's going to be the minimum. So what you want to do is just evaluate at 0, 7, 3, 6, 6, 3, and you're not going to know on this. You can't do this stuff in your head. You have to work out the details. So the objective function is P is 20x plus 10y. So you're just going to plug into each one of these things, and whichever the biggest one is the maximum. Okay, and this is the easiest part of the problem right here. Once you've done all the work, it's just now a matter of doing the arithmetic and seeing which one's the biggest. Okay, now a lot of this stuff you'll be able to do in your head. You can use your calculator on any part of this that you want to. So this first one, 0, 7, that looks like that would be 70. Second one, 3, 6, that'd be 60 plus 60, that's 120. The third one would be 6, 3, so that would be 120 plus 30 would be 150, so I think that's probably it. Then the next one is 7, 0, that's 140. Okay, so there is your maximum right there. You really can't tell by looking, so that's your maximum, like that. Okay, the only thing that made that problem any different was the fact that we had 3 inequalities instead of 2. So we had an extra corner point in there. That's the idea. Okay, all right, tell me, graphing. Is graphing okay? Figuring out the shaded region, is that okay? All right. All right, it's usually easy if they're all less than or all greater than. Other than that, you got to draw your graphs really clear. How about the last step? Everybody clear when you have to do a matrix to figure out a corner point? Okay, all right, yeah, you got to do that to figure out the intersection point. That's the simplest way to show you how to do that. Okay, well, let's go ahead and I'm going to go ahead and just do this one word problem here on the next page where you kind of put this together. Now, this is kind of what I'm wanting you to do. I won't do the 3 inequalities. I'll test you over kind of the ones that have the 2. Okay, so you want to definitely know how to do that. Okay, let's do this one. This one's fairly easy to do because it's already set up in the table. So this is the first example that we are looking with, I think. So I want to just kind of go through and put this whole thing together. All right, so we kind of looked at this at the beginning of the section. So what we want to do with this one is put the whole thing together. So basically, X was the trick skis and Y was the slalom skis. It's the same example that we started with, like that. So when I say I want you to get the decision variables, that's what X and Y are. Okay, so X in this problem is going to be how many of each type of ski should be manufactured. So we're going to say X is the number of the trick skis. Okay, then we're going to say Y is the number of the slalom skis. The only thing that makes this problem any different is you have to read the word problem and you got to put it all together yourself. So that's what we're trying to lead up to. Okay, the objective function is what is being maximized or minimized. Okay, that has to do with profit. So if you read the problem on here, what it says, and this may be a little bit different than the first problem, it says the profit is $40 on a trick ski, $30 on a slalom ski. So that means the profit is $40 for every trick ski, which is X, plus $30 on every slalom ski, which is Y. Now, what do you do with that objective function? That's what you plug the corner points in. That's what that's doing. That's what makes it a linear programming problem. Now what you're going to do is look at your table, and the table will pretty much tell you what your inequality is. So what you're going to have is you're going to have an equation for each row. It's going to go like this. You'll have 6x. That just means every trick ski requires 6 hours of labor to fabricate it, and then plus 4y. What that means is every slalom ski requires 4 hours of labor to put it together, fabricating the materials. And the constraint is that's a maximum number of labor hours, so that's less than or equal to 108. Okay, like that. The second row is the same thing. It would be 1x plus 1y less than or equal to 24. And then you have these things. You have to pay attention to this, really. You can just say x comma y is greater than 0. They have to be positive values, because what that is that's the number of things you're producing. Okay, so when you do a word problem, that's what makes it different. You have to figure out the objective function and the constraining conditions, but once you do that, it's all identical to what we've been working on anyway. Okay, so what we would do with this one then is we would do the graphing. Now I'm not going to go through on the graphing. I'm just going to show you this. I'm going to scan up to the first page, and I think this was the same problem anyway. Or no, I guess those are different numbers, aren't they? I thought I had given you the same numbers, but I guess not. Okay, so let's put this together. We have 6x plus 4y less than or equal to 108. The second equation is x plus y less than or equal to 24. So to finish this up, we want to just go ahead and get our graphs, and then we want to get our feasible region and then evaluate the corner points to finish this up. Okay, now on this, see what I'm going to do on this is I'm just going to do 6x equals 108, and I'm going to do 4y equals 108 to get the intercepts. And I'll do this on my calculator. So 108 divided by 6 is 18, so that's an x-intercept. 108 divided by 4 is 27, so we need to make our y-axis go up to 27. And then over here, x is 24 is the x-intercept, y is 24 is the y-intercept, like that. Okay, so we got everything we need. It's two less than problems, so you already know your feasible region is going to be kind of down in the corner then. Okay, so let's see. I'm just going to kind of do something like this. I'm going to just maybe make every 3 5 or something like that. 1, 2, 3, 10. 1, 2, 3, 15. However you want to do this is up to you. Okay, that'll take me out to 25, and that'll get everything fit on here. I'm just going every 3 is 5. Okay, so that's good enough. Okay, all we got to do is get a pretty good estimation of this anyway. So this first line is going to have an x-intercept of 18, just estimate it, doesn't have to be perfect. Y-intercept of 27, so it's going to go like that. Second equation has intercepts of 24, so it'll go like that. So we get that, okay. We have two less thans, so that means the feasible region is down below like this. Okay, so what we got to do next after we do that is we got to figure out our corner points, and then we have to evaluate the profit when we put that together then, like this, okay? Okay, so let's see, the corner points. We have 0, 0. This one is the y-intercept on that I think was 24. So this corner point right here is 0, 24. So that's a corner point. This corner point here is 18, 0. Just look at your graph to figure that out. And then you want to do the matrix. So when you do this corner point, you're going to do the matrix 6, 4, 108, 1, 1, 24. Has anybody done that yet?
Yeah, 618.
What did you get?
618.
618? Okay, I'll take your word for it then.
These
Okay.
are the same numbers that we had in 5.2.
Yeah, it may be. Yeah, it may be. So that's fine. Okay, so we got that. All right, now what we do is we plug into the objective function, and then we're done. You can bypass the 0, 0 because we're finding maximum profit. So you would just plug in the 24. So that would be P equals 40 times 0 plus 30 times 24. Then plug in the 18, 0. So that would be P equals 40 times 18 plus 30 times 0. And then do the 618. So that would be 40 times 6 plus 30 times 18. Okay, and we'll just figure out which one's the biggest. So the first one is 30 times 24. So this first one is 720. That's profit. The second one is 40 times 18. So that's also 720, so it's a tie. And then the last one is 40 times 6 plus 30 times 18. So that one's 780. Okay, so that is where your max profit is. Okay, all right, I got kind of in a hurry on that towards the end, but that's the idea. Okay, now anybody that wants to attend Math 93 on Wednesday can. And what we're going to do is I did a video. Let me just explain kind of what I did this morning.